Okay. Roll number 241. Just now I told you that please stop your video and mute your mic. Okay. Please, all of you, let me know. Is my screen is visible to you? Is my screen is visible to you? Everyone,
Sir.
okay, okay,
Sir.
okay. Now, please. Now, today's topic is representation of a discrete time signal. Till now, we have seen okay, representation of a discrete signal. See, until now we have seen only the continuous time signals and how the continuous time signals are basically classified and how many types of continuous time signals are available, and we have seen so many test signals which are easily generated in our laboratories. Now we are going to see the important representation of the discrete time signals. Now see, there are four types of representations which are available for representing discrete time signals. Out of those four representations, the first one is graphical representation, second one is functional representation, third one is tabular representation, and the fourth one is sequential representation. Out of all these representations, sequential representation is very, very important, and 99% of the cases we are representing the discrete time signals, okay, with the use of sequential type of representation. Sequential type of representation. Okay, see, now see the first one, graphical representation. So before going to see this graphical representation, first of all, you people should remember that the discrete time signal is represented with the x of n. X of n. Now see here. See, in some textbooks, we are using the arrows for representing the discrete time signals, or sometimes we are also going to represent the same discrete signal with the like this. See, I am going to represent the same graphical representation of x of n. Now see here. So this is amplitude 1 and this is amplitude 2. Okay. Now see here. So at x of 0, the amplitude of the x of n is given by 2. Okay. This is 0. This is 1. This is 2. This is 3. And on x-axis, I am considering n. Now see here, I am going to represent the amplitudes at various instants of time. I am drawing the same signal x of n. Okay. I am drawing the same signal x of n. There is no difference at all. But the only difference is the representation of a sample. Okay. Sometimes I am using the arrows here. Or in some cases, I am going to represent the same amplitude with this one. Okay. Instead of arrow, I am going to represent the sample like this also. So at 2, the magnitude of x of n is equal to 1. Okay. Similarly, at 3, so at 3, 1.5. And at a -1, this is the case. Now, please try to understand the difference between this type of graphical representation and this type of graphical representation. Both are of same type graphical representations only. In this particular case, I am representing each and every sample with a straight line having some arrow on the upper point. But in this particular case, there is no arrow, but the sample representation is only like this, like this. Okay. So this you will see in various textbooks, right? So whatever it may be, but both the type of representation of the samples is same. Okay. So graphical representation, what we are going to see in the graphical representation. Now see here, let the discrete time signal has the values as x of -1 is equal to 1. That means at n is equal to -1, that signal x of n is having magnitude is equal to 1. Now see here. Okay, at x of 0 is equal to 2. That means at n is equal to 0, that signal is having magnitude 2. At n is equal to 1, that signal x of n is having magnitude is equal to 2. At n is equal to 2, that signal is having magnitude at 0.5. At n is equal to 3, that signal is having magnitude of 1.5. That means only at n is equal to -1, 0, 1, 2, 3, the signal x of n is defined. And for all the remaining values of n, that signal is not defined. That means what are the two consecutive samples here? So one sample is at n is equal to -1 and another sample is at n is equal to 0. In between these two consecutive samples, you don't have any information. Okay, you have missed information here. So this is the type of discrete time signal representation. This is one type of representation of discrete time signal. Okay. So similarly, functional representation. See, all types of representation already you have studied in your mathematics. Okay, nothing new in it. Okay, you people are very much familiar with the concepts of this type of representations. So what is the difference between graphical representation and functional representation? So here x of -1, x of 1, x of 3, x of 0, x of 2 is given, and by using these values you can draw the graphical representation. But in the case of functional representation, he is directly mentioning that x of n is equal to 1 for n is equal to -1, x of n is equal to 2 for n is equal to 0. Similarly, x of n is equal to 2 for n is equal to 1, which is equal to 0.5 for n is equal to 2, which is equal to 1.5 for n is equal to 3. Okay, so you need not draw the graphical representation here. Why? Because it is a functional representation. You have to mention each and every value in terms of function. X of n is equal to some n. Okay, so that is the functional representation. Okay, next we are going to see next type of representation. That next type of representation is tabular representation. That means you have to mention, okay, you have to mention wait, right. Now see here, tabular representation. So at n is equal to -1, 0, 1, 2, 3, x of n is equal to 1, 2, 2.5, 1.5. So everything you are going to mention in a tabular column. So for the value of n is equal to -1, x of n is equal to 1. See, this is not the different case. This is the case of previous example. So previous case we have defined so many values of n and x of n also. Now see here, this is the example which is the common example for each and every representation. So graphical representation same, functional representation same example. Similarly, tabular representation is also having the same example. And the last one and very important type of representation of a discrete time signal is sequential representation. sequential representation. So what is a sequential representation? Now I'm going to explain this type of representation in clear, right? Just wait. I'm using whiteboard. Please let me know. Is my screen is visible to you? Roll number 211 respond. 18 series 211. 18 series 211. Is my screen is visible? See, I am sharing my whiteboard here. Anyone respond,
Yes, sir.
please?
Yes, sir.
Yes, sir.
Okay, thank you. See here, now I am sharing my whiteboard here. Now I am going to explain the sequential representation. This is a very, very important representation. Okay. Sequential representation. So what is sequence? Okay. So till now we have seen x of 0 is equal to, sorry, or you consider this one also, x of n is equal to 1, which is equal to 2, which is also equal to 2. Now I am considering functional representation. This is not the sequential representation. This is only the functional representation. Okay. Please try to understand it clear. 0.5 and this one is 1.5. Okay. This is at n is equal to 0. This is at n is equal to 1. And this is at n is equal to 2. N is equal to 3. At this is, sorry, I think this is n is equal to -1, right? This is at n is equal to -1, 0, 1, 2, 3. Okay. This is the functional representation. Just now we have seen. Now we are going to study about the sequential representation. How this signal x of n is going to be represented in a sequential form. This sequential type of representation. This is a very, very important type of representation. Now you please all of you see here. Now how I am going to write down the same x of n in sequential form of representation. Now x of n is equal to, so please observe it very carefully. Why? Because sequential representation always starts with a sequence, like curly braces. Curly braces. Now you need to mention. Now you need to mention the amplitude 1, 2, 2, 0.5, 1.5. Now you just close this sequential representation. Now very, very important point here is you need to write arrow at this particular point. All of you clear? So the sequential representation is x of n is equal to 1, 2, 2.5, 1.5. Now what this arrow indicates, there is a special meaning in the case of sequential representation. If you are using an arrow, arrow is nothing but the arrow indicates that is the starting point. That means your sequence is starting at n is equal to 0. So left side points are negative values of n, and right side values are positive values of n. If you are representing an arrow at this particular point, at this particular place means now this is the value of x of n at n is equal to 0. Now this is 1, 2, 3, and the left values are negative values. So n is equal to -1, x of n is equal to 1. Now this is the very, very important type of representation. Okay, is it clear? If anyone is having any doubts, you please ask me at this moment. X of n is equal to the sequential form of 1, 2, 2.5, 1.5. Now this arrow indicates that that is the starting element or the starting point. So at n is equal to 0, that x of n value is equal to 2. So is it clear? N is equal to 0, x of n is equal to 2. Suppose, okay, you will have one important doubt in your mind that, sir, what happens if some cases the arrow is not given? That means in that particular case, by the default, you need to consider the starting point is the starting magnitude is the starting point. That means you need to consider arrow at the first point. Suppose if he has not given the arrow, okay, if he has not given or if he has not mentioned anything about the starting point in this particular sequence, you need to consider this first point as the starting point. Okay, this is by default case, you need to consider the first element as a starting point. Okay, is it clear? Is it clear, everyone? Please respond.
Yes, sir.
Okay, thank you. So now see here, sequential representation. A finite duration sequence with the time origin n is equal to 0 is indicated by the symbol arrow. So just now I told you that whenever we are representing arrow in the sequential representation means that is the starting point, n is equal to 0. Okay. So a finite sequence can also be represented like this. Suppose if it is the case, x of n is equal to 0.2, 1, -1, 3. That means at n is equal to 0, x of n is having magnitude 1. N is equal to 1, x of n is having magnitude -1. And n is equal to 2, x of n is equal to 3. N is equal to 3, x of n is equal to 2. Likewise, we are going to represent the discrete time signal, right? Now see here, basic discrete time signals. Okay, already we have seen basic continuous time signals. Okay, unit step signal or unit step function, unit parabolic function, unit ramp function, unit impulse signal, all the signals we have seen. Already we have seen in the case of continuous time signals, right? Now again, same in the discrete time signals are also, again you are going to define the same signals, but the representation is different. Now see here, I am going to explain the basic important differentiation between unit step sequence or unit step signal in the case of continuous and in the case of discrete time signal also. Now see here, unit step sequence is defined as u of n is equal to 1 for n greater than 0 and u of n is equal to 0 for n less than 0. That means from n is equal to 0 to infinity. So here remember that n is an integer. N is equal to 0, 1, 2, 3, 4. It is not 1.5 or it is not 2.5. So n is integer means either it is 0, 1, 2, 3, 4, etc. up to infinity. Okay. So from 0 to infinity, that's value is equal to 1. Now see here, I have represented the magnitude here. So all the samples are having equal magnitude, that is equal to 1 from 0 to infinity. And from minus infinity to 0, that signal is having the magnitude is equal to 0. Suppose if it is a continuous time signal, now please try to understand the difference between continuous time signal and a discrete time signal. So in the case of continuous time signal, we are going to define the unit step signal as u of t is equal to 1 for t greater than or equal to 0, which is equal to 0 otherwise or t less than 0. See, t less than 0 or otherwise or elsewhere, both are same. Now see the mathematical expression. This is also the mathematical expression. U of n is equal to 1 for n greater than or equal to 0, and which is equal to 0 for n less than 0. This is also the mathematical expression, okay, for discrete time signal, and this is a mathematical expression for continuous time signal. U of t is equal to 1 for t greater than or equal to 0, and u of t is equal to 0 for t less than 0. Now see the graphical representation of u of t signal here. Graphical representation of u of t signal here. So this is the case. So this is u of t u of t for t is equal to 0 to infinity. Now what about the signal which is from minus infinity to 0? That signal is already defined, that is equal to 0. Now please try to understand the difference between unit step sequence and unit step signal. This is in the case of continuous time signals, and this is in the case of discrete time signal. Now see the graphical representation also. So always there is a discontinuity in discrete time signals, but there is no discontinuity in a continuous time signal, and this is the basic important differentiation between continuous time signals and discrete time signals. Okay, now we are going to see one more type of signal, that is next one is unit ramp sequence. Unit ramp sequence. Some anyone please respond, what is the unit ramp? What is the mathematical representation of a unit ramp signal or unit ramp function in the case of continuous time signal? Anyone, any one of you please respond. Any one of you please respond.
R of t is equal to t.
Okay, please speak loudly. Yes, correct. Speak loudly. R of t is equal to?
T, sir.
Yes, R of t is equal to t for t greater than or equal to 0, and which is equal to 0 for t less than 0. Now please try to understand the difference, clear difference between the discrete time signals and the continuous time signals. Okay, once if you are familiar with the continuous time signals concept, obviously it is also very easy to understand discrete time signals concepts also. The only differentiation between discrete and continuous is the representation. So here N stands for discrete case, T stands for continuous time case. Now in this particular case also you will get the slope is equal to 1. Okay, so from 0 to infinity it is a, now see here, it is a linear one, it is a linear one. Okay, now the next one is unit impulse signal. Unit impulse signal. Now here I need to explain the very important point or very important difference between delta of n and delta of t. Now please see here. So in the case of unit impulse signal in the continuous time, it is also marked as delta of t, delta of t, delta of t is equal to 1 for t is equal to 0, which is equal to 0 for t is not equal to 0. What is the difference between this continuous time signal representation and discrete time signal representation? In both the cases, you are having the value at only n is equal to 0 in the case of discrete and t is equal to 0 in the case of continuous time case. But here, one important doubt has to rise in your mind. Sir, what is the difference between delta of t and delta of n? delta of t is continuous time signal, delta of n is a discrete time signal. But in both the cases, the mathematical representation says that delta of t is equal to 1 at t is equal to 0. Is it a continuous? Is it a continuous or discrete? Is it a continuous signal or discrete? That is a very important doubt you have to arise in your mind. So in this particular case also, the original signal is like this. The original signal is like this. So delta of t, now see here, you are having a small pulse at t time t is equal to 0. This is the original representation. So which is consisting of a small pulse duration, and let us consider that pulse duration p is equal to imaginary very negligible, very small negligible pulse duration are approximately p is equal to 0. If we make p is equal to 0, then the duration of the pulse is equal to 0 means obviously this will be converted into a sample. This is the original signal, and this is obtained once if we make the pulse duration p is equal to 0. This is the basic difference between continuous time impulse signal and a discrete time impulse signal. In both the cases, the values are existing only at n is equal to 0 and t is equal to 0, and for the remaining values of time, that signal is not defined. Okay, understand? Now here I will solve one or two problems for you people. Okay, and I will give you the remaining problems are as an examples. Now please all of you see here, delta of n. Any one of you please respond for my sake. Please let me know how many of you are know the answer. First problem is, see, do you understand what I am saying? Anyone respond, please respond. Do you understand what I am saying? So till now we have represented only, or till now we have discussed about the types of representations of a discrete time signals and different discrete time signals which are available. Now we are going to solve a problem here for you people. So here the first one is, I'm going to solve the first problem. Now see here, e power 2n multiplied by delta of n minus 2. Now what's the value of this? Evaluate the function. Suppose if you are getting this type of problems in your external examination, so how will you solve this? How will you solve this problem? Sigma n is equal to minus infinity to plus infinity, e power 2n multiplied by delta of n minus 2. Already we have solved this type of problem in the continuous time case. Integral n t is equal to minus infinity to plus infinity, e power delta t into delta of t. Right? Already we have seen this type of problems in the continuous time case. Can anyone tell me what is the answer for this? What is the answer for this question? Any one of you, please respond. Okay, I will solve this problem for you people. So suppose if you are getting this type of functions, now please clearly see this problem. This is the multiplication of two signals. The first one is e power 2n and the second one is delta of n minus 2. Suppose if any function that is multiplied by an impulse function, you will get only that function only at a prescribed time instant. That means here delta of n minus 2 is equal to the basic standard definition as per discrete time signal. Delta of n minus 2 is equal to 1. That is the impulse signal which is having the magnitude only at n minus 2 is equal to 0, and which is equal to 0 otherwise. Now please try to understand the concept. So here we are multiplying an exponential signal with the impulse signal. So here you need to remember the original definition of impulse signal. As per the definition of impulse signal, delta of n minus 2 is equal to 1 for n minus 2 is equal to 0, and which is equal to 0 otherwise. Now we can consider this as n is equal to 2. That means that signal is only having value at n is equal to 2. And for the remaining values of time, that is n, that signal is not defined. That means you need not evaluate the function from minus infinity to plus infinity. So instead of measuring this function from minus infinity to plus infinity, just you substitute n is equal to 2 in this function. So e power 2n, e power 2n at n is equal to 2. Now what's the value? Which is equal to e power 4. Now you try to calculate e power 4 value in your calculator. So that is the solution. So the first problem is e power 4. This is the answer. Now please tell me the answer for this one. Please tell me the answer for this one. Sigma minus infinity to plus infinity, delta of n minus 1 into e power n square. E power n square. So yes, exactly correct. Why? Because delta of n minus 1 is equal to 1 only at n is equal to 1. And for the remaining values of n, that signal is not defined. Means you will get e power n square at n is equal to 1. At n is equal to 1. That means you will get e. So this is the solution. Now in this way you are going to solve the problems. Okay. Now once again I am going to share my whiteboard here. Please see here. Now please see here. Now I am going to explain a very important point, how we are going to represent a unit step signal in terms of unit sample signal, unit impulse signals. Okay, now see here. Now please all of you see here. Now I am drawing a waveform. See, this is delta of n and this is delta of n minus 1 and this is delta of n minus 2 and this is delta of n minus 3 and this is delta of n minus 4. Only for our convenience I am considering only up to n is equal to 4. Okay. Now what is the value of delta of n at n is equal to 0? That means here at n is equal to 0 will have the magnitude is equal to 1. Now delay this delta of n by 1 unit. That means now this is the case. This is 0, n is equal to 0. This is delayed unit impulse signal. Unit means obviously the amplitude is always equal to 1. Now what is the, now again delay this signal delta of n minus 1 by 1 more unit. Obviously you will get a delta of n minus 2 is equal to 1 at n is equal to 2. Now again delay the above signal by 1 more unit. So you will get this one 3. Now delay delta of n minus 3 by 1 more unit. So at delta of n minus 4 is equal to 1 at n is equal to 4. Likewise, we will go on up to k or up to infinity also. Okay. Now you combine all the values from n is equal to 0 to infinity. What you will get? If you combine all the values from n is equal to 0 to infinity, what you will get? Now see here, just I am combining all the values of delta of n from 0 to infinity. Now at n is equal to 0, this is 0, this is 1, this is 2, this is 3, and this is 4, and up to infinity. Now see here, this is 1. At n is equal to 0, delta of n is equal to 1. Now, see, I'm adding all the values of impulse signal from n is equal to 0 to infinity. Now see here, is it not? Am I correctly drawing? Anyone, you please respond.
Sir.
Okay, just I have added all the samples from n is equal to 0 to infinity. Now tell me what type of representation it is? What type of representation it is? What type of representation it is? Or what type
Continuous.
of definition? No, it is not continuous or it is not discrete. I am defining a new function from impulse signal, that is u of n. What is the basic definition of u of n?
Step. Unit step.
See, it is not a graphical representation or it is not anything else. Okay, so just now I have added all the samples from n is equal to 0 to infinity. That means by combining all the sampled values, all the samples, you will get a u of n. The basic definition of u of n is equal to 1 for n greater than or equal to 0, which is equal to 0 elsewhere or otherwise. That means u of n can be obtained from unit impulse signal as sigma n is equal to 0 to infinity or now see here. See, I am converting this n to k. Now see here. Please all of you look at this. U of n can be obtained from unit impulse signals as u of n is equal to sigma k is equal to 0 to infinity delta of n minus k. Now substitute various values of k from 0 to infinity. So first you substitute k is equal to 0. What you will get? Delta of n. That is defined only at n is equal to 0. Similarly, next if you substitute k is equal to 1 means obviously delta of n minus 1. That is you will get this one. You will get this one. Impulse signal which is delayed by 1 unit. If you substitute k is equal to 2, you will get impulse signal which is delayed by 2 units. If you substitute 3, you will get a impulse signal delayed by 3 units. If you substitute 4, you will get the delayed signal which is delayed by 4 units. Likewise, you are going to get the unit step signal from an impulse signal. So that is why I am explaining this on a whiteboard. Okay. Now see here, with this we have completed the problems based on this one. Next one is very, very important question. Basic operations performed on signals. What do you mean by operation? Why we are doing operations? Suppose if you are taking a human body, if you are getting a disease, or if a person X is having some operation. Okay, what is the main aim of doing operation? Somebody has broken their hand or some injury has caused very serious damage to the health. Okay. In that particular case, he or she needs an immediate surgery. What is the need of doing surgery? Suppose if the bone is fractured in the leg, what is the need of doing surgery to the leg? Anyone? Just to perform the operations normally. Okay. Without doing surgery, we cannot be able to do the work normally. So that is why in that particular case, an operation is required, okay, to perform the functions on the regular basis. Okay, in this particular case also, you have to do some operations on these signals such that to get the required content from the signals. Okay, so in those particular concept or in that particular concept, the basic operations performed on the signals are given by time shifting, time reversal, time scaling, amplitude scaling, signal multiplication, and signal additions. So these are the main important 6 operations which are to be performed on the signals. Okay. So in each and every operation, I am going to explain continuous time case and also discrete time case. Okay. So please try to understand the concept. First one is time shifting. As I already told you that, excuse me, as I already told you that most of the times, by seeing the name of the title, you are going to get some information. You are going to understand the content in that particular topic. Time shifting. That means the time has been shifted to a new value. Let us consider the signal x of t, which is as shown. Roll number 41. Why are you always leaving the class? If you repeat the same, I don't want to admit you people, right? See, once if you, excuse me, so let us discuss those points at the end of the session. Now, please let us consider a signal x of t as shown in figure. Time shifting of a signal may delay or advance the signal in time, and mathematically it can be represented by y of t is equal to x of t minus capital T. See, already I announced the particular words, or I told you the delay and advancement in the signals, okay, in the previous classes. So please try to remember the words delay or advance. Okay, delay means suppose if you are considering x of t signal here, delay means it is going towards plus infinity. Advancement means obviously it is going towards minus infinity. Only if your time is positive. Time is positive. If the time is negative, obviously delay becomes advancement and advancement becomes delay. That means if you are moving towards minus infinity, that is delay, and if you are moving towards positive infinity, it is advanced. That is the basic difference between, yeah, okay, positive symbol of time. Now see here. Here, a signal x of t is represented like this. Okay, like this. If this particular signal is advanced by 1 unit. Okay, just now I told you that advancement in the case of positive times means it is moving towards minus infinity. Okay, and delay means obviously you must delay this signal by t units. That means it moves towards plus infinity. Okay, this is the basic signal. And if the signal is advanced by t units, that means let us substitute t is equal to plus 1. T plus 1. That means capital T is equal to 1. That means you are going to substitute this with minus 1. Again, if t is equal to 1, if you substitute this one, obviously you must make t is equal to 1. Okay, so this basic signal is delayed by 1 unit, you will get this one. If the same signal is advanced by 1 unit, you will get this one. Okay, for you people, for the sake of you people, I am going to explain one more example here. Now see here, this is x of t, which is defined from 0 to 1. Okay, this is x of t. This is t. Now I am asked to represent the same signal, okay, by consider the delay of 2 units. That means I am asked to represent the signal x of t minus 2. T minus 2. See here. See here. This signal is basically defined only at or only from 0 to 1. This is an interval 0 to 1. But you are asked to draw the same signal by considering a delay of 2 units. Now, let us discuss how the shape of the waveform if you delay the same signal by 2 units. Now see here. Now see here. Now what is the starting point? What is the starting point? What is the starting point? So here, suppose if you want to delay the signal by 1 unit, means obviously this will be delayed by 1 unit. So the signal is like this from 1 to 2. The signal is defined from 1 to 2. But here you are asked to delay the same signal with 2 units. That means now this is the case 2 to 3. So during the first step, the signal is delayed by 1 unit, means obviously the signal is defined from 1 to 2. In the second step, the same signal is delayed by 1 more unit. Obviously, your signal will start from 2 to 3. Okay, 2 to 3. Now, again you are asked to represent the same signal x of t by taking some advancement by 1 unit. So here, see here, x of t plus 1, t plus 1. T plus 1. That means now your signal will starts from. Now see here, this is the basic one. Please try to forget about this one. What is the basic signal? Basic signal is defined from 0 to 1 only. If the signal is advanced by 1 unit, means obviously you will be able to get the signal which is defined from -1 to 0. Okay, this is delayed by 2 units and this is advanced by 1 unit. This is the basic example of this particular case. Okay. Do you understand? Anyone, you please respond. Do you understand?
Yes, sir.
Yes, sir.
Okay, this is the time
Yes,
shifting operation which is performed on a continuous time
Sir.
signal. Suppose if the same type of operation which is performed on the discrete case, let us see. Now see here. Similarly, for the discrete time signal, the time shifting operation is given by y of n is equal to x of n minus k. Now, in this particular case, A, B, C, 3 cases are given. The first one is x of n. This is the basic version, basic signal you have been given. X of n is given, which is defined at n is equal to 0, 1, 2, 3. Now you are asked to delay the same signal with 2 units and advance the same signal with 3 units. Now, how do you get x of n minus 2? If you consider delay of 2 units for this particular base signal. Now see the starting point. Instead of starting the signal from 0 to 3, now your signal is defined from 2 to 5. 2 to 5. Just you need to delay the same signal by 2 units. So instead of starting n is equal to 0, now your starting point is at n is equal to 2, and remaining amplitudes are same. There is no change in amplitude. So similarly, if you want to delay the same signal x of n by 3 units, now see here, now your basic signal will be advanced by 3 units, means now your signal will start from -3 and ends at 0. Okay, so that's all for today. Remaining we will continue it in the next class. But please do remember, please try to